Hello everyone, this is Vasant, a nine-pointer at IIT Bombay from the Department of Civil Engineering. In previous lecture, we started the new topic that is pure bending. In continuation to that lecture, we are going to discuss topics of pure bending. So in yesterday's lecture, we already said that in one observation, every cross section comprises of tension and compression in longitudinal direction, right? Tension tension and compression over here, tension over here, right? So at every cross section it comprises of tension and compression. So that means the length, initially the length is L, this length is L, so the length is getting shortened at upper region and the length is getting elongated in the lower region. This indicates that there are longitudinal strains, right? Because there is the change in length. And we also should take note that the longitudinal strain is varying along y direction, because here the length is shortened, here the length is elongated, and in between the length is undeformed. So the longitudinal strain is varying along y direction. In today's lecture, we are going to discuss that topic. So if you take the beam and consider a line EF, so of length dx, see this S is the neutral surface, okay? This is neutral surface, मीन्स इसका डिफॉर्मेशन नहीं होगा, मतलब जो लेंथ पहले बेंडिंग के एप्लीकेशन के पहले जो लेंथ है वही लेंथ आफ्टर बेंडिंग विल हैव ओके. So this is dx length, so this will be also dx length, right? So if you take mn section and pq section, so this ef length will be dx and this length also will be dx, right? So now we are applying bending moment upwards like this. So the deformed beam will look like this, right? So that we drawn over here the deformed beam. So in the deformed beam, we already said that the line present in the neutral surface will not undergo any deformations. So if you take, this is the neutral surface, so this length will remain as dx again. And we already know that mn is one cross section, pq is one cross section. So that cross section just will go like this. We already said that the cross section will remain plane. The plane before deformation and after deformation will remain plane. So that mn will look like a straight line again, but it is somewhat tilted, right? So that is represented over here. This is m1 tilted one and this is pq tilted one. So at a distance y we consider ef. So the deformed ef will something look like this, right? So one thing you need to observe, so this arc, this small length dx ka arc will subtend some angle d theta at the center, right? So the radius of curvature should be measured from the neutral surface. This is a big takeaway, that we will solve one problem that you will understand the importance of this point. So we should measure this from neutral surface. So this is rho. The radius of curvature is rho. So see, what is initial length EF? Initial length EF is dx, right? Right. So what is final length? The final length will be, see, initial length is dx, that will be is equals to rho into d theta, right? Because this distance is rho and its subtended angle d theta. And final length is dx dash, that will be is equals to, see here this length will be is equals to nearly rho minus y. See, actually it will be some cos theta term will have, because this is y, we need to subtract this one, but we already said the deflections are small, so this distance will be y only. So we can write it as rho minus y into d theta. Do you agree? Right? So we already know that strain epsilon x is given by change in length divided by original length. So what is the change in length? Dx dash minus dx divided by dx, right? So dx dash is rho minus y into d theta minus dx is rho d theta divided by dx. Dx is rho d theta, right? So we get this is minus y d theta divided by rho d theta. So this will give us minus kappa y epsilon x. So in these pure bending concepts, do not bother about the sign convention. Just calculate the value in terms of magnitude and by intuition put the sign. By intuition put the sign, because see we got epsilon x is equals to minus kappa into y, right? Because we got that, because we applied movements like this, so the curvature is like this, so it is compressed one, top one is compressed, right? So the strain should be negative. But if you apply bending movements like this, now if the top portion is in elongation, so for that same value of y, now you will get kappa into y. So the value of strains are changing with the different directional application of the bending moments, right? So never bother about the signs in first calculate the magnitude, then by intuition put the signs. So we are getting epsilon x is equals to kappa into y. So we should write epsilon x mod. So modulus magnitude of epsilon x will be modulus of kappa into y. Okay. Just took this one. So in that case, we are getting kappa into y, but there also, if you see what the radius of the curvature will be negative in that case, right? Because it is downwards at that case, it is upwards at that case, right? So in this case, the radius of curvature is positive for upward bending moment diagram, and y is above, so we are getting positive one. Now we are getting negative one, right? So in that case, the y is above, but the kappa is negative, right? So we will get positive one. So just I am saying that don't bother about the signs, just go with the intuition. So if you see the longitudinal strains derivation, it is purely based on the geometry of the deformed beam, right? We just derived the longitudinal strains by the geometry of the deformed beams. We never included the properties of the material, means such as Young's modulus. So we can say that the strains in a beam in pure bending vary linearly with distance. Yes, it is varying linearly with distance because kappa is constant in pure bending case, that we will see in future lecture. This is y, so it is varying linearly with y. So with distance from the neutral surface, yes, from the neutral surface it is varying. So regardless of the shape of the stress strain curve of the material, means it is independent of the stress strain curve, whether it is whether it is following Hooke's law, not following Hooke's law, doesn't matter. The longitudinal strains are epsilon x is equals to kappa into y magnitude in pure bending case. But in normal stresses, the stress strain curve will matter, right? Because epsilon x is independent, but in normal stresses the stress strain will matter. See, for linearly elastic materials, and homogeneous one, linearly elastic, homogeneous and isotropic materials, the stress strain relationship will be sigma x will be is equals to E into epsilon x. Do you agree? Right? So we already derived epsilon x, that is minus kappa into y. So that will be is equals to minus E into kappa into y, sigma x. Again, don't bother about the signs, just go with the intuition. So mod sigma x will be is equals to mod E into kappa into y. So this is the stress variation in the cross section. So the stress variation will look like this, right? If you apply bending moment like this, then it is going compression over here, tension over here. So here it will be compressive stress. Here in the bottom it will be tensile stress. That is clear. Now we said that there will be some surface where there will be no deformation, but where will that surface will there? That we need to locate, right? So that we are now going to look at. See, in the material, we doesn't apply any axial forces in the beam, right? So the net axial force should be 0. That is clear. So if you see over here, Because of the bending, normal stresses are developed. So the net force due to these normal stresses should be zero at the cross section. So if you take small element dA, if you take sigma x into dA, sigma x is force per unit area into that dA element will give dF. So integration of that should give us 0. So that is minus epsilon kappa into y dA. So for a homogeneous and isotropic material with single value of E on the whole cross section, this E is constant for that type of material. So this kappa is radius of curvature is constant for pure bending. So the location of the neutral surface will be given by integral y dA is equals to 0. What this represents? This represents centroid of the cross section. Okay. So for pure bending with a single value of E of homogeneous and isotropic material, the neutral axis will pass through the centroid of the cross section. Okay. With this, we end today's lecture. In next lecture, we are going to discuss this pure bending in some more details. So if you like this lecture, do subscribe to our channel, Ninepointer. Thank you.